here, and today I'll be talking about the different forms of the line. So we talked about the line so far, right? We know there's a collection of points, but there's a more compact way to write a line in vector notation, and it's known as the vector equation, and that will be r equals to a plus lambda b, where lambda is any real number. It's a set of all real, so in fact it spans across all real numbers. So yeah, so usually you give the question will give us, if you want to define a line, then you have a x, a y, a z. You have the coordinates, you have the components of the a vector as well as the b vector. So this will be bx, by, bz. Okay, so that's the vector equation for a line. Today we're going to learn about other forms of a line. Namely, there's one more, there's two more. One is called a parametric, and another one is called the Cartesian. So we learn how to convert between different forms of the lines. And why is this important? Well, simply put, sometimes the question gives you one form and you need to convert to the other. But it's also important that if we can understand the other forms, then we have a stronger understanding of what it means for what it means to be a line. Okay, so yeah, so the vector equation we have gone through in quite a lot of detail, right? We know that if there's a line, then to describe it, we can give the location, we can give the position of one point on the line, right? So that would be described by the vector A, right? And then we can specify a directional vector on top of the one position on the line, one point on the line. We can specify a directional vector B, right? And note that note that the A can be any point on the line, and the B can be any directional vector that's parallel to the line. So any vector that's parallel to the line will work for B. Then after that, by writing this equation, we will generate the entire line, because by scaling B with lambda, right, by any real number, we essentially walk along the entire line. Also for lambda equals to 1 is this, for lambda equals to 2 is this. And everywhere in between lambda equals to 1.1, lambda equals 1.2, it will generate along the entire line. And if we let lambda span across all the real numbers, then we'll generate the entire line all the way from lambda equals to minus infinity to lambda equals to infinity. So that spans the entire line. Okay, so that's what we know so far. Yeah. Okay, so another way to look at it, right? So if we write, if we write r equals to x, y, and z, right? Because x, y, and z are the coordinates of the points on the line, then we can actually arrive at we can actually get x, y, z equals to ax, ay, az plus lambda bx, by, bz, where lambda is real number. So if we equate each of the components, right, then for the x component we get that the x coordinate of a point on the line equals to ax plus lambda bx, and then for the y it's also likewise, and for the z is also similar. So these are just extracting the components of this equation. Okay, so it comes from the vector equation here, and lambda is a real number. So you can so this is known as the parametric equation, because the lambda is a parameter. So this is the parameter. So what this means is that the lambda, you can think of it as a parameter that you vary. So what this means is that to generate the entire line, right, if you're familiar with parametric equations, then to generate the entire line, we set lambda equals to, or we let lambda be all the values. So that means we let lambda equals to, let's say, -1, then that will generate then we substitute lambda equals to -1 into these three equations, then we get x, y, z. So let's say we get x, y, z equals to, let's just say it's 1, 1, 1. Let's just say it's -1, -2, -3. Okay, then we substitute lambda equals to 0, then let's just say x, y, and z is going to be 0, 0, 0, then we substitute lambda equals to 1, then let's just say we substitute inside, then x, y, and z is going to be 1, 2, 3, and so on. And for every value of lambda that we substitute into these three equations, right? For every value of lambda we substitute into these three equations, we're going to get a set of a coordinate, right? A x, y, z coordinate for one point. Then we substitute all the values we can for lambda, all the real values into these three equations, and we'll get a whole bunch of points, and the whole bunch of points is going to be the points forming the line. So actually, right, the parametric equation is very similar to the vector equation. It's just extracting the components, extracting the coordinates x, y, and z out. Okay, so to convert between the two, just simply to convert the vector equation to the parametric equation, simply let the r vector equals to x, y, z like this, and then write it out component wise. And to go the other way, right, simply extract the coefficients of lambda, and that will form your b vector, and then extract the constant terms, and that will form your a vector. So I'll illustrate this with an example later. But let's move on to Cartesian. So from parametric equation, you can actually you can go an additional step to convert it to Cartesian equation. And to do so, we make lambda the subject of the formula. Make lambda the subject for all three equations. So what do we see? We see that for the first equation, right? For the first equation, we're going to get that lambda equals to x minus ax over bx, right? Then for the second equation, we're going to get, for the y component, we're going to get y minus ay over by. And for the third one, we're going to get z minus az over bz. And if we equate all these three lambda, right, because they must all be a common value of lambda, then we're going to get the Cartesian equation, which is this. So this is the Cartesian equation. It's known as the Cartesian equation for the line. And it might seem a bit weird, like where did the lambda disappear to? And the answer is that we need to reframe our thinking from one that is varying a lambda, right, to one that is talking about constraints on coordinates. So it's a nice time to talk about degrees of freedom, right? Degrees of freedom and slash constraints. Okay, so the way to properly understand this equation is to think in terms of constraints. So let's just say let's engage in a conversation, right, where I say that you can choose any x, y, and z coordinate that you want, anything. So you can choose any value of x you want, right? Let's say you choose 1, then you can choose any value of y you want. Let's say you choose 1, and then you can choose any value of z you want, and then let's say you choose 0. Okay, so then I can ask you to plot this point in space. So in this case, it'll be the 1, 1, 0 coordinate. It'll be a point in space with the coordinates 1, 1, 0. Then I can tell you to repeat this process again and again and again and again. And in the end, if you do this forever, then you have filled up the entire of the universe, right? Because if I give you any freedom, right? If I give you any freedom to choose any coordinate that you want for x, y, and z, then the space of possibilities that you can choose is just the entire universe. Like you can choose for every point in the universe, you can possibly choose that point. Okay, so that's in a sense you have 3 degrees of freedom, because there's 3 variables that you can choose, 3 coordinates that you can decide what you want it to be. Okay, so you can essentially choose 3 times. So degrees of freedom is kind of like number of times you can choose, right? Number of variables, in a sense, variables. Yeah. Okay, then let's say I tell you that let's say I say you can choose you can choose any three. Okay, so that's the first scenario. Then let's say we have a second scenario where I tell you can choose any three values. You can choose any three values of x, y, and z, right? Any value of x, y, z, except that you have a constraint that x equals to y. Okay, so this is a rather simple constraint, but yeah, there's this constraint. So then the question is, how many degrees of freedom are you left to choose? Well, let's say you go ahead and choose x equal to 1. Then when you look at y, when you want to choose y, you realize that in order to satisfy this constraint, it must be equals to 1. You cannot choose any other possible value of y. And then lastly, you can choose z equals anything you want. So you see that in the previous example, right, you have chosen x to be anything, you have chosen y to be anything, and z to be anything. For all you know, this could have been any value you want. It could have been 3, it could have been pi, it could have been e, any value you want. But in this case, you have chosen x freely, but then y was constrained, right? Y was constrained, so you couldn't choose y freely, but then you can choose z freely. So there's 2 degrees of freedom that you can choose, 2 variables that you can choose to your liking. Okay, and we see that there's one constraint. Yeah, and if we sum this up, then we see that there's a total of 3 dimensions. Okay, so yeah, so you could also ask the question, is there more interesting constraints I can write? And the answer is yes. You could write, for example, x equals to 2y. Alright, in this case, then this would need to be half, right? Or you could write x equals to 2y plus 1. In this case, y would need to be 0. Yeah, but there is a limitation to what we're talking about. We need this constraint to be a linear constraint, because if we write something like x equals to y squared, then it's a bit tricky, because then your y can technically be plus minus 1, but we don't want to deal with any of that. So in this case, it needs to be a linear constraint, which basically means that it's a linear equation in y. There's no squaring and stuff. Okay, so if it's a linear constraint, then yeah, it could be like x equals to 3y plus 2, or so on. But the point is, right, if we have one constraint, 2 degrees of freedom, you add them up, you get 3. So let's imagine a third scenario now. Let's say we have 2 constraints. Right, let's say we have x equals to 2y and equals to, let's say, 3z. Then you can, if you try to choose freely again, right, then you can start off with one choice. Okay, yeah, so you can start off with one choice, right? So for example, you choose x equals to, let's say you like the number 6, right? But then as soon as you fix x to be 6, right, so x was a free choice. But as soon as you choose x equals to 6, then by the constraint over here, right, y is automatically determined for you, right? In this case, y equals to 3, and z is also automatically determined for you, equals to 2. And if you happen to choose another value, so let's say I choose 12, then y is also automatically determined, and z is also automatically determined. So yeah, so what's the point in saying all this? Is because we have 2 constraints and we end up having 1 degree of freedom. So you see that the constraints plus degree of freedom always adds up to 3, which is the number of dimensions we have in our space, right? In our space, in our universe. Number of space dimensions we have in our universe. Yeah, so actually the equation above here is just example of 2 constraints and 1 degree of freedom. And this 1 degree of freedom precisely is the line degree of freedom. So yeah, so I want you to imagine another picture, right? Imagine that initially we start off from a universe that we can choose any. It's just it is the universe, right? And initially, with 3 degrees of freedom, the the space of possible values of x, y, and z is the entire universe, right? Every single point in the universe can be chosen. However, we add one constraint, right? Let's say we add a constraint of x minus 1 over 2 equals to y minus 3 over 5, let's say, right? Then we have cut down by 1 degree of freedom, so we are left with 2 degrees of freedom. So what we actually specify now is a plane. So it's actually a plane in this 3D universe. The plane stretches to infinity, but I can't really draw that, right? So it's a 2D slice of the entire universe. We've sliced the entire universe using a 2D plane, and now we can only choose points on that plane. Now we're constrained to that plane, because as soon as we choose one coordinate on the plane, as soon as we choose one x coordinate, right, we have automatically determined y coordinate, and then the z coordinate is can be anything we want. So so in the end you end up getting a plane, which the plane represents all the possible choices of points you can choose respecting this constraint, respecting this equation. And lastly, if we choose to add an additional constraint, right, so now we end up having we end up having two constraints. We're having two constraints. So for example, we have equals to z, let's say equals to z, right? So then once we choose one value of x, right, we automatically determine the value of y and z. And we choose another value of x, we automatically determine y and z. Let's say when I choose the value of z, then as soon as we choose the value of z, it automatically determines for me x and y. So you can see that whichever variable I choose first, right, if I choose x, then it leads to y and z being determined. If I choose y, then it leads to x and z being determined. If I choose z, it leads to x and y being determined from this equation. And so, in the end, we can only have 1 degree of freedom, and that 1 degree of freedom is precisely a line. So that the only degree of freedom left, right, is where on the line do we want to choose our point. And that is precisely what this Cartesian equation is trying to get at. Okay, so I hope that this has cleared up some understanding, right, regarding why the lambda seems to have disappeared, and that is because we're talking about a different kind of way of thinking now. Instead of thinking of the lambda representing the freedom along the line, we're now starting off, right, with 3 degrees of freedom and adding 2 constraints. Yeah. So yeah. Now one last question, right? What if one of the b's is 0? What if, let's say, bx equals to 0? Then wouldn't lambda equal to x minus ax over bx wouldn't make sense. It'll break down. And in fact, that is true, because if bx equals to 0, then if we take a look at our equation, our parametric equation, then actually that would mean that x equals to ax, and this is actually a constraint by itself. So we no longer need it's still at one constraint, but it's just no longer participating in this equation with y and z. But this is actually a constraint in itself, because we're saying x must be fixed at this value ax, which is a constant. Okay, so in the next video we'll be starting to talk about applications of using applications of line equations, and we'll be starting to do some questions with it. Bye.